So, Daniel Soukup will tell us something about ladder systems.
Yes.
I have the exact title, but we'll
Yeah. So thank you very much. So the plan is that I'm going to talk about new aspects of ladder system uniformization. And I'm going to start with some old aspects and some history. Okay, so it looks like that I'm going to have time today and 2 weeks from now to talk about this thing. So I'm going to start with a very slow-paced introduction to give you the classical results about ladder system uniformization and why are these important, how they turned up, and what people have been doing so far. And hopefully at the end of talk today, I'm going to outline the results that I was working on in the last 6 months, year, and then prove some of these new results in the next time. So yeah, today is mostly background for that.
You speak again in 2 weeks, is that correct?
It looks like, yeah. Okay, so let's start. We're going to be working all the time on omega 1 and with ladder systems on omega 1. So yeah, please stop me at any time. I'm really trying to make everything accessible and understandable, so that you can actually follow if you wish. Working on omega 1.
What's omega 1? No, that's a joke.
Omega 1 is the set of countable ordinals, and pick some gamma set of limit ordinals. This is where I'm going to take my ladder. So let's define a ladder system on gamma. Gamma is some set of limit ordinals. A ladder system on gamma is just a sequence of sets C alpha indexed by gamma, such that C alpha is a cofinal type omega subset of alpha. This is alpha, and C alpha converges up to alpha like this. Okay. So C alpha is a subset of alpha. Supremum of C alpha is alpha, and type C alpha is omega. Right? Usual thing.
Do they have to be disjoint or anything?
Sorry?
Do they have to be disjoint or anything?
No, but that's a very good point. They are always almost disjoint, right? So if you have alpha and beta here, C alpha goes up to alpha, C beta goes up to beta, so they might have some common intersection with this, with C alpha, but from some point on, all but finitely many elements of C beta are going to be above C alpha. Right? Right? So usually we're interested in ladder systems living on at least stationary subsets, but I'm not assuming anything of gamma at this point. Okay, so what we're going to do is we're going to color ladder systems. Okay. So let's say that these C's are going to be denoted by C bar. C bar is a ladder system. So a coloring of C bar is a sequence of maps, again indexed by gamma, such that each F alpha individually locally colors C alpha. Okay, we're going to color with n colors. N is 2, 3, 4, whatever, or omega usually. Okay, so at most countably many colors. Okay, so we have ladder systems, and we have a coloring of a ladder system. Okay, so now we're at this point where each of the letters is locally colored. Okay, and right, so C alpha, the coloring at C alpha and the coloring at C beta may disagree, right? Something like this. But each letter is individually colored. I'm just saying that the domains might intersect. They might have a common point.
Have a different color. When green stands for coloring, not a color.
Yeah.
So this is the green. The green graph is supposed to be F beta, and the blue one is F alpha. Their domains might intersect, and at common point they might differ. That's what I'm saying. Now these colorings can have uniformization. So what is a uniformization? A uniformization of this F bar coloring is a global map phi on, say, all of omega 1, which agrees with all of these functions almost everywhere. Is some map phi such that for any alpha in gamma, phi restricted C alpha almost equals F alpha. Bless you. In other words, the set of xi in C alpha where F alpha xi doesn't equal phi xi, is finite. I'm not saying that such thing necessarily exists, but any function which has these properties is called a uniformization. Right, so you can imagine if, for example, gamma has two elements, alpha and beta, I can do the following. I can take f of alpha below alpha and then cut f beta at alpha and then let phi be the rest. Okay, so for example, that's a good choice. Phi equals f alpha union f beta minus alpha. This would be a uniformization for just these two functions. Right? It completely agrees with f alpha, and it might have some disagreement with f beta down here, but otherwise it's equal. Right? Any questions? No? Yes, the question is, I mean, the main question we're interested in was when does a uniformization exist, right? Yep. So this is, we're gonna look at this.
Pieces, you have them, right?
Yes, exactly. So that's what I'm about to say. So let's see when uniformizations exist. If gamma is countable, then any coloring has a uniformization. Okay, so this is the first result. Moreover, if gamma is non-stationary, then the same holds. Again, any coloring okay, so imagine that we have a fixed letter system on gamma. Okay, just to warm up, let's prove these results. So there's a very natural partial order which forces a uniformization. Okay, these are all ZFC results, but let's just look at this problem that way. So let's define, given a coloring f, we define a partial order. So elements of this P sub f are going to be functions P, so that the domain of P is a finite union of letters, union C alpha, alpha in some finite set Fp, and P almost everywhere agrees with these functions. P restricted to C alpha, almost the same as F alpha for all these finitely many. And extension is just extension S functions. So the stronger conditions are larger. Larger functions. So the thing is that if I have a domain like that, if I have a condition and I look at its domain, right, it's going to be finitely many letters, the union of finitely many letters like this. And I look at some beta, right, this might look like this. And if I take a beta, which is in gamma, but not already in the in our domain in this finite set, then C beta intersection this domain is still finite. So this is just a small observation.
You mean the union of the C's attached to the?
Yes.
Oh, I'm sorry.
Yeah, so if I have a condition that's a function defined on finitely many letters, and if I want to add another letter to this, I'm saying you can do this because this new letter only intersects in finitely many places. So what you do is, if you want to add beta to the domain, you just define Q to be union whatever P was, the domain of Q to be the domain of P union C beta, and Q on these new points, C beta minus domain of P, is going to be, by definition, FB, exactly. Well, minus whatever it is on the same set. Right? So you can always add an extra point, right? Points can be added to new points. Great. So how does the first result follow from this? What's the one line ending to the proof?
Just keep adding points.
Well, yeah, but that's sort of unprecise. Yeah. Exactly. Yeah, that's what I wanted to hear. That is, that if you have a partial order and countably many dense sets, then you can find a filter, which means all those countably many dense sets. Yeah, it's Martin for Aleph-0 many dense sets, and it's true in ZFC.
Why did it take 2 people to prove?
One was giving dense sets,
So this implies that you can find, if gamma is countable, just meet all F0 dense sets with filter G, and P. This, well, quite weak, but still enough generic enough filter, generic G will be the uniformization. Okay, and how do you get the second result from the first?
Take a club avoiding the stationary set.
Exactly.
And the supremum of the club below the point that you want to deal with is bounded. So then, I mean, you do what you did before.
Exactly. Yeah. So you have a club C. If gamma is non-stationary, then you have a club which is completely disjoint from gamma. Okay, so that means that there is this partition of omega 1 into intervals by points in the club. So alpha 0, alpha 1, alpha 2, and so on. And whenever I'm exactly at one of these alphas, there is no ladder attached there. Okay, there's some points here where I see ladders going up in between, but no ladders at these alphas. So you can apply at each countable interval the first part. So I have this gamma 1, gamma 0, these countable sets of coordinates, where I can apply the first fact. This is countable. So 1 applies to find the phi 1 uniformization in this interval, phi 0 in this interval, and so on. And if you just put these together, that's a uniformization for the whole thing. Okay? And you never run into trouble because a ladder from an interval here only meets all these smaller intervals in at most finitely many points. Okay. Is a uniformization for the whole thing. Okay, so this was the sketch for that.
So, I'm asking something cumulative gas. Is it true that if the ladder can be uniformized, in some outer model universe, then this forcing it doesn't collapse in closure? Would you like to force with this? You may collapse omega 1.
So it's true.
Is this the universal method for coloring the ladder?
So this always uniform. The ladder system uniformization is so weak that you can always do it without collapsing omega 1. So that's perfect because that's what I wanted to say next. This forcing is always CCC. Yeah. Well, this is in some sense finite. Well, there's very little information about any uniformization. I mean, okay. What's the information in the poset?
You need f of p, and then you need where the coloring starts to.
Exactly. Yeah, and that's just a finite information. Yeah. Yeah, so it looks like an infinite condition, but in reality, it's completely it's equivalent to forcing with finite conditions. PF is always CCC, so if you have always CCC, so theorem. Yeah, so That's true. If I use more than
one color, then you have these.
more than countably many colors, then this might not be CCC.
Oh.
For
Oh, I see.
countable
Yeah.
colorings.
Conditional color.
No, it takes the color that's already underlined and just has to say it.
Oh, you're right.
One,
You're
two,
You're given the color.
yes.
So under Martin's axiom, any letter system coloring, well, omega coloring, has a uniformization. That I'm only allowed to use countably many colors.
No, n was 2, 3 up to omega.
Yeah. So, but I just want to, emphasize that you're only allowed to use countably many colors. Countably many colors. Yeah, I know I said that each coloring is going to be countable, but still. Yeah. Okay, so the base of the ladder can be anything. It can be stationary. It can be club. It can be a whole of omega 1. Any ladder system coloring will have a uniformization. I'm not proving that the forcing is CCC, but it is. Any questions? So if not, then the next thing I want to look into is non-uniformization results. So this is one side that if the letter is small or you have some kind of axiom that helps you, then you always have this uniformization property. No matter how the local colorings are given, you can always find a global one agreeing with all the locals almost everywhere. Now let's see some non-uniformization results.
Sorry, is the fact that it's CCC, does it involve something clever, or is it like a delta system argument?
No, it's really just a delta system argument. Okay, so if Martin's axiom implies this, then you try diamond, and that's gonna work. Okay. So diamond on gamma implies that for any ladder system C on gamma, there is a 2 coloring without uniformization. Okay, so if diamond holds on this set gamma, and I'm going to explain what diamond on gamma is, then no matter how the ladder system is given, you can always locally color it with 2 colors such that there's no global function uniformizing. Okay, so let's see this quickly. Okay, so what is diamond on gamma? So this means that there is a sequence S alpha, a guessing sequence, again indexed by gamma, such that for any subset of omega on X, there is an alpha in gamma where X is guessed, X intersection alpha is S alpha. And this implies that gamma is stationary.
And it will be stationary.
Yes, so the immediately from the fact that you guess every set at least 1, you have guessing on stationary many. So it's the same as if you wrote stationary here. There is stationary many. And there are many applications of these types of axioms. And usually what happens is that you're not just guessing subsets of omega 1, but you're guessing functions, you're guessing various structures like trees or topological spaces or anything that lives on or can be defined on omega 1 and has this property of initial segments being countable. So how I'm going to use this is I'm going to guess functions. For any global function, let's say let's use phi already. For any global function, there is stationary many alpha, such that S alpha guesses this, so I can just write phi restricted alpha equals S alpha. Okay, so diamond 4 functions, diamond 4 sets, these are all the same axioms. Okay, so now given a ladder system C, this is what we do. We define F alpha C alpha 2 as follows. So I look at S alpha. If S alpha happens to be a function, then I look at its restriction to C alpha. Often this is going to guess a global function. Okay? Okay, so this is a function. Suppose that this is a function that goes from C alpha to 2. Okay, let's assume that it only takes 2 values. If this happens, in this case, take some, let's say, minimal I, either 0 or 1, such that this value is assumed infinitely often. S alpha minus 1, whatever, I on this set C alpha is infinite. Right, so I look at this guessing function. It takes values 0 and 1 on C alpha. Let's assume that this happens. Then I look at which value appears infinitely often. This is some value I. Okay? And what I'm going to do is I'm going to say that let F alpha be constant 1 minus I, the other number. If I was 0, then this is going to be 1. If I was 1, then this F alpha is going to be 0, the other value. I claim that this sequence now has no uniformization. And the proof is that if I take a global function, no matter how I take a global function, then there must be an alpha in gamma where phi restricted to alpha is guessed by the diamond sequence. Okay, so phi restricted alpha is C alpha. In fact, phi restricted C alpha is the same as S alpha restricted to C alpha. And in this case, phi assumes this I value that we talked before infinitely often. This equals I infinitely often. But the local coloring was exactly defined the other way, right? It's the other value everywhere. Okay, so phi and F alpha disagree infinitely often at these places. So F alpha does not almost equal this. Exactly. Yes. So that's a perfect question. So diamond was enough question, is CH enough to carry out something like that? And the answer is yes, but it's very far from the usual or typical CH applications in some sense. At least, you know, at that time when people were thinking about this, this was a very big step. So yeah, we're going to get to the CH thing in a second.
You're saying CH gives you a very weak diamond.
Exactly. So what happened is that people realized that in order to carry out the same proof, you don't need the full strength of diamond. So you can write down a fairly technical statement which resembles a guessing principle, or which is a guessing principle. And it turns out that it follows from CH. And that's enough to carry out this proof. But the reason I stated this diamond argument is so corollary that if V equals L, then C on gamma has the uniformization property, or any coloring can be uniformized, unif property, if and only if gamma is non-stationary. Right, one thing, if gamma is non-stationary, this was the first fact that we saw. But if gamma is stationary, then from this assumption you get that diamond gamma holds for any stationary. And so you have a non-uniformizable coloring. Right? So exactly these, only these trivial, very thin letters can be uniformized. Okay, so I think this whole letter system uniformization is a very nice combinatorial problem. But the reason people were looking at this was that it had very important applications. So I think when this was discovered or first defined was around the Whitehead problem. Okay, so this is a question in algebra, in group theory. So let's look at abelian groups. I can't write abelian.
Like diamond, but just a subset.
Mm-hmm.
You guess.
And not necessarily your club suit, you mean? So is the guessing attached to alpha or just anywhere?
Oh, I'm sorry, maybe it's called club. It's like for any subset, you have stationary many places where it is a subset of it.
Yeah, that's club suit. So whether that is enough,
No, but it doesn't imply CH.
yeah, so there are these models where you don't have CH, but you have
Actually,
this.
CH plus this thing is a diamond.
Yeah, yeah. So I'm not sure, I should know this, and I'm going to look it up, but I don't know it on the top of my head. So one place where CH fails, so you might have uniformization, is the sex model, side-by-side sex. And I mean, there you have club suit. That's why I'm saying this. And I don't know what happens with uniformization there. Yeah, so, but the thing is that uniformization to fail, it's enough to have weak diamonds, these weak parametrized diamonds, parameterized with these cardinal characteristics, this Jamonia, Prusak, Moore type of things. And those usually hold when the Yeah, so I don't know. The answer is I don't know. Okay, sorry. Yeah. Okay, so abelian groups. Just a few words about this problem. An abelian group is free if the following happens. It's free if and only if any epimorphism splits. So whenever I take a surjective map from H to G, then you can find theta, yes, such that the composition is the identity on G, so theta B splits if this happens. Good. Now a group is called Whitehead, just a Whitehead group, if a very restrictive class of epimorphism split, if, so now this is the definition, if any epi psi or sigma with kernel integers splits. Okay. So the usual notion of being free as an abelian group is equivalent to this property, that whenever you take this surjective homomorphism, it can be inversed.
What's the usual property? I don't know what the usual definition
That you just, it's just, you know, you can take a set of generators, and G is a group, free abelian group over those generators. Yeah. Yeah, yeah, yeah. Okay.
It means it's a diamond sum of copies.
So this is a bit more restrictive, right? You're not asking for all epimorphisms to split, but just ones with a very special kernel. And the question is every Whitehead group free? So this is a major question in group theory in the 50s, 60s, I guess. And with time, people realized that every countable Whitehead group is free. And it was Shella who showed that it's independent, ZFC, whether every Whitehead group of size LF1 is free. It's independent of ZFC if all W groups of size LF1.
What about Aronszajn?
Yeah, I'm not sure. So if the, how is this? Again, this is something that I should know. I don't know. The only thing I know right now is that if there's a counterexample that has regular size, because that was another like big milestone in set theory, that was a singular cardinal compactness. That these non-freeness examples, the smallest ones, cannot be singular. If you have a singular structure of a structure of singular size and all its smaller substructures are free, then the whole thing is free. But anyways, the important thing here was that being free, or well, the existence of these Whitehead groups or counterexamples can be characterized by letter system uniformization. So let me write this down. So in the 70s, Shella showed this independence, but didn't realize this connection with uniformization yet, or we didn't define this uniformization yet. And later in the 80s, he was looking at the Whitehead problem together with CH. Whether CH decides if all Whitehead groups are free or not.
But always for groups of size.
Again, groups of size LF1. Yeah. And the following are equivalent. So this is also Shella. So this is in the 80s, and this is in the 70s. Yeah, I don't know the number of these papers. So the following are equivalent. One, there is a non-free Whitehead group of size LF1. And two, there is a ladder system on a stationary set. C on stationary gamma with the uniformization property, such that any two coloring can be uniformized.
Two colorings different from 1 to 3 coloring and 4 coloring?
Yes. Any two coloring can be uniformized. Yes. Consistently, you can have a ladder system where all two colorings are uniformized, but not all 1,000 coloring uniformized. So if there's a big enough gap between the numbers, then you can prove a theorem. So this is in one of these Whitehead problem with CH papers, but I don't think there is a proof which is readable anywhere. I mean, this is outlined in one of Shella's papers, but if you look at that proof, it's extremely circular. And I think it can be done, but I with good heart I wouldn't say that it's written down.
So your answer to David's question was
consistently, probably yes.
There is a ladder system
Where if you only use
property for colors for two colorings, but
not for 1,000. Yeah.
But what about when you quantify overall systems?
If you have ladder if you can uniformize any two coloring on any ladder system, then you can uniformize any omega coloring on any ladder system.
So in particular in this statement, you could put anything in?
Yeah. No. This is just for one ladder system. This is for one fixed ladder. You have, yeah. So the thing is that if you can thin out the ladder, you can code a lot of things, or more like add more things than code one. Yeah. Okay, so if there is a stationary set with the ladder that you have uniformization, then there is a counterexample. So under MA, there is a counterexample. There is a non-free W group of size LF1. And in the constructible universe, there are no such examples. Yeah. Unfortunately, I don't know anything more about Whitehead groups, so. The topologist? It's a natural question. I mean, the question itself, whether Whitehead group is free, I mean, the two definitions are really close. And I think at that point, it was really unexpected that that independence would just pop up in that field. Yeah.
I didn't mean why did they care about Shella's answer. I was wondering why they cared to begin with.
Probably they didn't, yeah. Maybe they didn't care about the answer, but they. cared about the problem more. But yeah, I don't know why they cared about the problem. Yeah. But ladder system uniform.
This is not the same as not CH. That's important. Right?
Yeah. Yeah.
It's not some familiar.
Yeah.
It's a new notion that characterizes.
Yeah. The thing is that here you have so CH is okay with the statement as long as the complement of gamma is stationary too. Yeah. So that's what I want to talk next about uniformization and CH. So there are many other examples of applications. Uniformization comes up in various topological examples. It comes up in some interesting graph theory and chromatic number problems. But I like to talk more about the basic combinatorics and the basic forcing results, consistency results about uniformization. All right, so we saw that diamond is enough to get, diamond gives coloring without uniformization. The question is CH enough? The answer is yes. Theorem CH implies that for any ladder system that lives on a club, with gamma club, or at least containing a closed unbounded set club, there is a coloring, two coloring without uniformization. And this two coloring can also be chosen very simple. In the last example, in the diamond example, the colorings were so-called monochromatic, that each ladder was simply assigned a constant function. Right? So the local colorings can actually be colorings, like depending on what positions are you in the ladder. And they can be just a single color. Okay, every point in this ladder gets the same color. Right? And if the uniformization property or the existence of uniformization fails even for these very simple colorings.
Anyway, so far the ladder hasn't played any role, right? You're just saying,
The individual, yes, yeah. It's always the base set, always the or the index set.
domain,
Yeah, just the domain.
Does the choice of ladder ever make a difference?
It makes when for your question, yes. So if you have the fact that you have uniformization for any ladder and two colors, then you have uniformization for any ladder and omega colors. Using different ladders can be used to code more colors. Yeah. Exactly. So this is quite important historically, because that was when Devlin and Shella introduced this so-called weak diamond. So what they showed that if you start that 2 to the LF0 is less than 2 to the LF1, which is weaker than CH, then this implies the following. Okay, so this is, for example, CH. Then the following holds. I'm going to write down the statement and then explain what it means. For any function that maps countable sequences of 0, 1 to 0 and 1, there is a guessing function, omega 1 to 2, such that along any branch, for any f in omega 1 to 2, the following set, those alphas, such that if I look at f, the branch at alpha, evaluate capital F, I get the same value as g of alpha. This set is stationary. Okay.
This is actually equivalent, or is it
Exactly. So this statement, I want to leave this later, but this statement is actually equivalent to that, which is quite surprising. I mean, this looks totally random and nothing like a cardinal assumption like this. Yeah, so let's try to decipher it. I'm not sure if I'm going to use this later, but it's a good thing to understand why this is a diamond. So first, for any f which assigns 0 or 1 to these countable sequences, so I have this gigantic tree, 2 to the less than omega 1. So each element in the tree is a countable sequence of zeros and ones. Think of this as the initial segments, possible initial segments for some large structure. Okay? So f tells you yes or no. Does this structure have a certain property? Okay. For example, if this were colorings, then f tells you, is this coloring infinitely often 0 on a ladder? Is this coloring infinitely often 1 on a ladder? Just decide some yes or no question. Now, g is the guessing function on omega 1. So g lives on omega 1. And it has the following property, that whenever I take a branch through this tree, a true global size omega 1 object, this f, then very often, stationary often, g and f agree. If you read off what does capital F say about this initial segment, it says the same thing as g.
It looks stronger than mine.
Yeah, it's, well, yeah. Yes, so that's one thing, that you're only guessing sort of a yes or no question, not exactly telling me what that subset is, right? So diamond tells you what is the initial segment of that uncountable set at alpha. This tells you if that subset is bounded or unbounded, or if it has infinitely many elements in something or not. Yeah. Does this assumption sort of make sense? Okay. Great, so yeah, this was a great surprise. First of all, they were just looking at this uniformization proof using diamond and trying to find the minimal assumption that gets you the same proof. And you can do the same proof with this argument. Okay. And just as I said, what you do is somebody gives you a ladder and you define a capital F. Okay. For any initial segment, you look at, well, what value appears infinitely often on my ladder up to this initial segment. That's going to be the capital F value. G guesses this, then G gives you a coloring of the ladder. You color with the opposite value again. Then this part is the global uniformization, and then this thing tells you exactly the same as what diamond did.
As you said, it seems special to 2 colors.
It is very special to 2 colors because it's strictly stronger if you assume 3 colors. Yeah. Yeah, so that's a very important point, by the way, that if you put 3 colors, then that's stronger. It's a stronger assumption. Stronger. And actually, if you put continue many colors there, it's equivalent to diamond. Yeah. No, it doesn't apply by CH. It's not implied by CH. Okay, so the last thing before we get into the new aspects of letter system uniformization part is something still about CH and uniformization. So why is this important? Actually, you can, given a letter system coloring, you can force a uniformization without adding reals. Okay, so this is a remark in the end here. Given F coloring of C, there is PF, let's say star. So this is a nice proper poset. In the extension, you have a uniformization, so much like the other thing that I defined. F has a uniformization. And this is the important part. This forcing does not add new reals. So this C can be anything. This can be a letter system defined on a club. This can be a letter system defined at every limit ordinal. And what I'm saying here is that given any coloring of a letter system like that, there is a very nice proper forcing, so nothing is collapsed, size omega 1 if size omega, yes, if CH holds. Yeah. So it introduces uniformization, but it doesn't add any new reals. So yeah, it's a very surprising thing. This theorem says that whenever CH holds for every letter system, there is a 2 coloring without uniformization. So when you start forcing with this, what happens is that, okay, here's my letter system, CH holds, there's a coloring which doesn't have uniformization, force with this. Okay, then that's destroyed. But CH still holds, no new reals. Well, then there is another coloring which doesn't have uniformization, so you force again. And the thing is, you cannot catch your tail with an iteration of length F2 because this, in the end, the iteration of these things will add reals. The limits add reals. And the funny thing is that not the first omega many will not add reals. There's something with omega square or something where the first reals appear. But any iteration must iteration and well, any iteration, you know, when you start really enumerating the colorings.
So the white hat group doesn't, this group without a split, you could add a split by this function like that. Or maybe not, I don't know.
I mean, here, so to get a counterexample with CH, you want to get a letter system where which lives in a stationary set and any coloring can be uniformized. So the trick here is that this theorem only applies for letters on clubs. In the white hat thing, you're allowed to live on a stationary, and if the complement is stationary, then the iteration doesn't add reals. Iteration must add reals. Yes, this is a good point. If gamma is a club. If gamma is co-stationary, let's say stationary, co-stationary. So stationary implies proper, and co-stationary implies that no new reals in iteration. So if the complement of gamma is stationary, then there are no new reals even in the iteration. And this is actually a very nice argument, I think. It's also in the Whitehead groups with CH paper. This is pre-proper forcing, which means that he does the iteration by hand. And I think it was Abraham who wrote down the proof. So it's very nicely written down, very detailed. And you can get a lot of intuition for proper forcing from that paper. So I read about, or I knew about proper forcing in the definition, but didn't understand the word. But then you look at this proof. This is a forcing which is not sigma closed, but doesn't add new reals. And the whole fusion argument there really resembles the proper forcing things that came a decade later. It's a very, very nice, like, forcing history piece.
Do they use it with countable elementary submodels?
Yeah, but nothing really deep or anything. Yeah. And since you're not adding reals, I mean, even the conditions are in the ground model, everything is decided. So it's a very simple situation where you can understand a lot of things, or you practice or whatever. For me, that was very, very useful to understand forcing better. Any other questions? Yeah.
So, is this forcing just like countable approximations, and you prove that every countable elementary submodel has a complete master condition?
Exactly. Yeah. So the thing is, if you imagine, so this is omega-1, and a condition is just a countable approximation. So this function here, P, works for any ladder that lives up to its supremum. So up to and including this ladder up at the top. So you want to get a sequence of condition which goes up to some fixed set delta, which hits some dense sets. There is a ladder, you got to be careful, there is a ladder going up to delta typically. So you got to promise to follow certain values that appear by the function at delta. So if this thing was closed enough, there's going to be a lot of places where this is a model, and there's going to be other models m prime here. So what you have here is you want to go above this condition. You want to hit these two values and get the right values here and go into this dense set. So what you do, you extend a bit to get the right values here, and then you go into the dense set. So get the right values first, then in M0 go into the first set D0. You have another model M1, other dense set D1. You have finitely many values to satisfy. You do that, and after you hit the dense set. And that way you can get a fusion sequence. No, it's definitely not how that's proved. But actually, isn't like it's going to be, especially if I mean, if the complement of gamma is stationary, then this forcing is going to be close to limits that go up to the complement of gamma. So it's going to be complement of S closed or whatever. So it's going to be almost sigma closed. Okay, so here comes the new aspect, and that's uniformization on trees. Okay, so what types of trees are we talking about? So we're going to talk about trees T, trees of height omega-1. But no more restrictions, really. For example, omega-1 is a perfect tree of height omega 1. I mean, it's a perfectly fine tree of height omega 1. Right? It's a pretty boring tree. It has a single uncountable branch. No branching anywhere. But that's a tree of height omega 1. OK, other trees. I'm also going to look at this sigma q. Well, it has a lot of different names. So these are subsets of the rationals, which are well ordered as rational numbers. And bounded. So bounded in Q. Okay, and this with the initial segment relation, end segment relation. End extension, thank you. So this is a tree of size continuum. It splits to countably many nodes at every place. Size 2 to the L of 0. And typical levels also have size 2 to the L of 0. What else? It doesn't have any uncountable branches. So it's quite far from our silly omega 1 tree. Oh, and I should say this, it has height omega 1, of course. OK, so apart from these, we're going to look at Aronszajn and Soukup trees. So what are Aronszajn trees? Well, Aronszajn trees are trees of height omega 1 which have countable levels and no uncountable branches. Height omega 1, countable levels. So this guy there was not an Aronszajn tree. And no uncountable branch. So this was good, no uncountable branch, height omega 1, that was good, but the levels are gigantic. So that's why it's not an Aronszajn tree. But it contains a lot of Aronszajn trees. That's the usual place where people found the first Aronszajn trees. And we're going to look at Soukup trees too. Soukup trees are Aronszajn trees which doesn't even have uncountable anti-chains. Right? So the levels are very special anti-chains. In Aronszajn trees, they are countable. In Soukup trees, all anti-chains are countable. So these are Aronszajn trees plus countable anti-chains only. Right, so Aronszajn trees always exist in ZFC. We might even construct one. Soukup trees may or may not exist. So under MA, Soukup trees, MA plus non-CH, they don't exist. Say under diamond, they do. And CH is not enough to construct Soukup trees. Okay, so what do I mean by a subtree? A subset S of T is a, I'm going to say subtree. I'm going to mean a few things by this. If it's downward closed, and pruned. So downward closed means what it's supposed to mean, that if you have an element S in S and something below it in T, then it's also in S. Which means that T and S has the same level structure. So the alpha level in S is a subset of the alphas level in T. And prune means that if alpha less than beta less than, let's say, the height of T, and S is in S alpha, so the alphas level of S, then there is a T in S beta which extends S. Okay.
Are your trees all pruned or
Yeah, I'm gonna work with only those. Yeah. Right, so you have a large tree, and we're going to look at subtrees which satisfy that if you have an S here, and you look at all the things which are above it, on any level above that, you can pick something. Right, something like this. What is this? Yes, that doesn't look downward closed. Yeah. No, it's better. Okay, so now we're ready for the main definition. So again, take usual letter system on omega 1. C. Let's say it's on all the limit ordinals. We're only going to be interested from letter systems on everywhere or in a club subset. And take a coloring. A T uniformization of this coloring. Okay, so it should be a global map. It's going to be a global map, but not on omega 1, but a subtree of T is a map phi with the domain of phi being subtree of T with the following property. For every limit alpha, I'm going to write this down and then draw. For every limit alpha, for any S from that limit level, if I look at f alpha at some value psi, it's the same as phi applied to S restricted psi for almost every psi in C alpha. So for all but finitely many psi in the ladder system, in the ladder going up to alpha, we have this. If I read off the value in the local coloring, that's the same as reading off the phi, the global coloring value on the branch at the right level, on the branch given by S at the right level. Okay, so large T tree. Let me rethink this. Okay, so this is omega 1. This is T. and S should be a subtree. Okay, so there's a global function on a subtree, on a pruned subtree. Whatever, I'm only gonna use 2 colors, but doesn't matter. So that the following holds. If I look at limit level alpha, and I pick any element from that limit level, and I look at the branch, what happens? Okay, so I have, this is alpha, so there's a ladder going up to alpha. Right? And there's a local function on this ladder. Right? So the ladder gives you certain levels. At those positions, the global function should agree. Right, so if I had some ordinal psi here, then this guy here is just S restricted to psi. Yeah, my psi looks exactly like these functions. Right, so they should agree with these. Whatever. Right? So for the sequence of local colorings, I can find a single global coloring on a subtree. This is, fairly large chunk of T, such that if I look at a branch and look at the function there, it agrees almost everywhere with the global color. So the thing is that if I take another branch from the same level, the agreement might start later. That's perfectly fine. So it's fine that I have some different values by phi here, and the agreement with the same function just starts later on different branches. So it's quite a weak thing. Exactly. Yeah. These are like, yeah. That's a very good point. These are like approximations to a global, to real uniformization on omega 1. Yeah. Sorry. Exactly. Yeah. This is a large tree of attempts.
You have this parameter T that you start out with.
Yes. So that's a fixed tree. Yeah. Okay, so this looks like a very arbitrary generalization, or for me it looked like. And this was originally defined by Justin Moore in the, I think it was 2006, something, 2000s. And he used this notion to understand uncountable linear orders. Okay, so this is the second main uniformization application that I like to talk about. Before I say anything more about results on this T uniformization. By the way, if T is just omega 1, you get back the same thing, same property. Or if T has an omega 1, is that true? No, that's not necessarily true. But if S has an Aleph-1 branch, then you get an actual uniformization. So linear orders. So after Whitehead groups, this is the other application that I like to mention. So first observation, if you take an infinite linear order, then it either contains a copy of omega, an increasing infinite sequence, or an infinite decreasing sequence. And actually, these are the only two infinite minimal linear orders. Okay? Plus minus omega, only infinite minimal linear orders.
Why?
By minimal, I mean that these are the only things which embed into each of their suborders. So if you have an infinite linear order, it has a copy of omega or minus omega. If it's minimal, it should embed to omega or minus omega. But if it embeds there, then it actually is omega or minus omega, because it's isomorphic to any of its infinite suborders.
I think dependent choice is so, right? Dependent choice?
Well, yeah.
I'm not sure that was the background of the question. We're assuming ZFC.
Yeah, I'm assuming ZFC in this. Yeah. Yeah.
Actually, without any choice, you don't have any ladders.
Well, well, I don't have anything without choice. Yeah.
It's consistent with ZF. There are no ladders.
Oh yeah, probably. Yeah. I see. Yeah. I mean, for this must be a very weak assumption, though. Okay, so how about uncountable? What is the situation with uncountable? Minimal uncountable linear orders. Right, so this means that there's a very small two-element basis for infinite linear orders, right? Is there something similar for uncountable linear orders? Like any uncountable linear order embeds something of size LF1, so it's enough to. But is there, a finite basis? Is there, do we have a classification of all minimal linear orders there? For example, omega 1 and its reverse are always minimal. I mean, in any model, they are minimal linear orders. Right, again, minimal uncountable linear orders in the sense that they embed into any of their uncountable suborders. Yeah. So if you take a linear order, it might contain an uncountable set of reals, which always contains an uncountable Aleph1 dense set of reals. So you can look at those. Aleph1 dense sets of reals. So any uncountable linear order which embeds an uncountable set of reals must embed one of these guys. This just means that any interval is uncountable. Okay? So this is a giant set. What happens is that under PFA, there is a one-element basis. In fact, any element is a one-element basis. These things are all isomorphic.
So what is an R1 set?
Any interval is uncountable. Right? So it's just a set of reals with the property that whenever you pick two things, there are Aleph1 many things between them. Right? It's just the rational is one cardinal up.
So it has size exactly omega 1.
Exactly, yeah. And if somebody gives you any set of reals of size Aleph1, you just throw out the countable intervals. Right. The rest is an Aleph1 dense set of reals. Under CH, the situation is horrible. There's no finite basis. Actually, there's no basis of size less than 2 to the Aleph1. basis smaller 2 to the LF1. So 2 to the continuum, so as large as possible. If somebody gives you a set of reals, you can find 2 to the LF1 many non-isomorphic reals inside that. So CH makes this situation really chaotic.
I'm sorry, did you say if you don't embed omega 1 or its reverse, then you must embed this thing?
Nope. I'm just saying that this is another type. So you have.
Oh, there could be more here.
Yeah, but what I'm saying is that this class is minimal in the sense that this is a downwards closed class with respect to.
Does there always need to be a minimum one, not equal to omega 1 or?
That is a very good question, Jonathan, and I'm happy to answer that in a second because we're almost there. So there are linear orders which doesn't embed these guys and doesn't embed any LF1 dense sets of reals, and they're called Aronszajn. Aronszajn orders. These are by definition linear orders without uncountable reals, uncountable real suborder, an uncountable suborder of the reals. An uncountable yeah, or plus minus omega 1. So no uncountable suborder of the reals and no uncountable well-ordered subset. So the first two things you think about, right? These are what kind of linear? Yeah, first two things, yeah. First three, yeah, or first 2 to the LF1 many. CH chosen as the first 2 to the LF1 many things you think about. Yes, so these things exist. They always have size LF1. You can prove a few things about them. And they are very closely tied to Aronszajn trees. It's not too surprising that they're very close to Aronszajn trees. Exactly. You can turn a tree into a bit differently. So with the Suslin lines, you're usually looking at branches. With this construction, you're looking at more like ordering the tree itself, the nodes of the tree. So you do a lexicographic order. Any level will have an individual order, and you compare two branches. Where they first differ, and that. So like 2 to the omega, it's the same.
Can these Aronszajn orders be very different from each other, or are they?
Yes, they can be. Yeah. Under CH again, you have, wait, what am I saying? Yes, they can be very different. For example, under diamond, they can be very different. But it is possible that they're also isomorphic, pairwise isomorphic. Yeah. Wait, what am I saying? Yeah. No, that's not true. So again, under PFA, the situation becomes very simple. There is a 2-element basis. But consistently, there are many different. CH is not enough to get that. There are many non-isomorphic. There are more than 2.
Right, but that doesn't directly tell you something about a basis.
Yeah, I think basis of size. Yeah. Okay, so back to Jonathan's question. Is it possible, however, that we have the same situation that the only minimal linear orders are plus minus omega 1? So CH takes care of minimal reals. If CH holds, then there are no minimal uncountable real suborders. But if diamond holds, or actually if a strong diamond holds, then there is a minimal Aronszajn order. If diamond plus holds, then there is a minimal Aronszajn order. This is shown by Baumgartner. Basically by Baumgartner. Well, Baumgartner had a sketch, and then somebody found a mistake in it, then I corrected the mistake, but Baumgartner had the main ideas. Yeah, and what I like to tell you is that consistently, though, Moore showed that it's possible that the only minimal linear orders are these two. CH holds, and the only minimal uncountable linear orders are these guys. Okay, so how does this, why does this have to do anything with uniformization and uniformization on trees? Well, what Justin did, he showed that it's possible that CH holds, and whenever you have an Aronszajn-tree letter system and a coloring, then you do have a T uniformization. For any Aronszajn-tree T, for any letter system coloring F, there is a T uniformization. And these two things, CH plus this statement, implies that the only minimal uncountable linear orders are plus minus omega 1. Enough for previous result. Sorry? No. I think that was the main contribution in that paper. I mean, it's not easy to do this forcing argument, but it's relatively standard. But the thing to realize that if you have CH plus a tree with this property, then it cannot be minimal. It cannot be used to produce a minimal Aronszajn-tree. That's, yeah, it's a bit tricky. It's something, you know, CH is used as a weak diamond, and somehow this uniformization property prevents you to embed the tree into itself. That's the main idea there. Yeah. Yeah.
So the tree with the lexicographic ordering is the linear order?
Essentially, yeah. Yeah. And the embedding of linear orders corresponds to embedding of trees, at least, well, restricted to a club set of levels. Yeah. Okay, so how did I get here? Oh yeah, last remark. So this should at least surprise you a bit. CH and the weak diamond was always enough to produce a letter system without the usual uniformization, right? For any letter system, there is a coloring which doesn't have a uniformization on omega 1. But if you only have a tree, which, right, these trees don't contain long branches, you can find this special, you know, weak uniformization, right? So exactly what Jonathan said, that was a very, very good remark. This is only a tree of countable attempts, a tree of approximations. And this says that you can always do that and have CH at the same time. So the reason I started to look at these things was when Raphael was working on strongly surjective linear orders. And then I found this nice question of Baumgartner's. So he had this construction using diamond plus to produce a minimal Aronszajn order. Okay? So this paper, at the end, he asked many things, including about the finite basis for linear orders, no minimal linear orders, all these major big questions that have been answered by Justin. And there was a smaller question if a single Suslin tree is enough to do that construction. Right? So that diamond plus gives you a minimal Aronszajn order, and the way it's constructed, it's built on a Suslin tree. And Baumgartner asked if a single Suslin tree is enough to get a minimal Aronszajn order. So I was very happy to realize that nobody solved this question. And then I started looking into these things. So the first thing you'd like to do, for example, is that look at Justin's model. Right? So there are no minimal Aronszajn orders here. So this is the question. Is Suslin tree enough for minimal minimal Aronszajn order? So one thing I showed is that Justin's model doesn't have any Suslin trees. If CH holds, then for any Suslin tree, there is a ladder system coloring without uniformization. Actually, for any Suslin tree and for any ladder, there is a coloring F without T uniformization. In fact, Justin's model doesn't have any Suslin trees. So accidentally on the way, he is killing all the Suslin trees. However, it's still consistent with CH. Consistent with CH, plus there is a Suslin tree, plus only minimal linear orders are plus minus omega. Only minimal LO. So the answer to Baumgartner's question is no, the Suslin tree is not enough. You can have a model of, well, actually CH plus the existence of a Suslin tree, but no minimal Aronszajn orders. Actually, the only minimal linear orders are plus minus omega 1. So what I like to do next, this is essentially the end for today. Next time, I will talk about this uniformization property. So I'm not gonna show this result, but I'm gonna go back and look at this property and try to see the effect of various diamonds. Okay, and I'm just gonna state two results that I'm gonna show. And that's it. Yeah, so just while I'm erasing the board, so I was doing something similar to Justin's proof in the sense that I was uniformizing certain colorings, but the trick was that you had a fixed Suslin tree, and you only only found T uniformizations for those colorings where the Suslin tree doesn't embed into that given Aronszajn tree. Yep. So I had a version of Justin's theorem about uniformization, but in a restricted sense, I had CH, and for any Aronszajn tree that is very far from a fixed Souslin tree, I had the uniformization. So those trees are not going to help you define a minimal linear order, so you can forget about those. And you also have those trees which embed something looking like my own Souslin tree, but that Souslin tree was rigid, so it cannot be used to produce minimal linear orders. So you had a rigid Souslin tree and trees which looked like or embedded this rigid Souslin tree, and you also had other Aronszajn trees. But the Aronszajn trees had the uniformization property. Okay. Yeah, maybe I'm just going to finish. I'm going to restate the results anyways next time. And yeah. Thank you very much.
Monroe, you look like you're going to ask a question. No? Or any questions?
Yeah. Oh. Do you want me here? Yeah.
Coming back to the standard uniformization, does it make
Yeah.
sense to ask that you uniformize these colors on some stationary subset of the given one?
I think it would. So yeah. So you would have the property for any coloring. There is a substationary. Yeah. Yeah. No, that would totally make sense. Yeah.
Is that trivially true?
No, I don't think. So if you have this strong diamond where you're guessing on a club, then it's going to fail. But maybe it's consistent with diamond. That would be interesting, for example. Right, so diamond plus would negate what you're saying, where you're guessing, where your right guesses are happening on a club. But otherwise, it might even be consistent with diamond, which would be interesting. Yeah, sure. Tilo, you wanted to ask something?
Yes. So I have a historical terminology question.
Yeah.
Because so the weak diamond, so the antecedent of this equivalence, right?
Mm-hmm.
Not less than 2 to the half. And I think I've seen the negation of this being referred to as losing hypothesis sometimes, but I won't try to track it down. So
I saw this in this Stephan's paper, history of the continuum, he talks about this CH and losing hypothesis.
maybe I should look into this one. Because I found it, I had a feeling that there were not many sources, so I mean,
Yeah, no, I'm not good with his history. I mean, Asaf's diamond paper has some. Asaf Renault has this Servian diamonds. He talks about Servi, survey,
Oh, I heard Serbian.
no, survey
Serbian.
on diamonds.
And I would like to, also ask about the thing you said about coloring with 2 colors, 1,000 colors. So
Yeah.
there are some abstractions which are not quite clear what they are. Did I get that right? That no one actually sort of.
Yeah, so we have approved, a forcing argument, how to uniformize 2 colorings. If you look into the proof, you see that in the fusion argument, you're doing an induction which stops after whatever 2 to the 2 to the 2 to the 16 steps. And if you have enough colors, you can always somehow work against that induction. Yeah, so you can see how a circular argument is built from this. Yeah.
Let's say the opposite is open, so it could be that you can separate 2 from 3 and 3 from 4. So
Yeah. No, yeah, sure. Yeah.
I have a question.
Sure.
What about our 2?
Yeah, I'm sure Saran looked at it, and I'm sure there is something about it in the proper forcing book, but I never myself worked with this uniformization property there. I'm sure a lot of things go through just easily, and I'm sure there are points where it becomes really interesting in the sense that it's not just a straightforward generalization. Situation is a bit different because the non-CH already implies diamond on uncountables, so it's gonna be a bit different.
Right, you get some automatic
Yes,
diamonds
yeah.
too. That's
Yeah.
True, but not on the top
Yeah.
of finality.
Yeah, and also I don't know about the different cofinalities, so
The diamond you get is on cofomega, not on cofomega.
yeah, yeah, yes.
There is a question. I mean, there's a somewhat, I think, obvious way where you can have, instead of the ladder system, look at a coloring on T. Or
You
something like that. I don't know exactly how it would work.
so in you would so you can ask for the global function to be defined on T.
Yeah.
That would make sense. Or the ladder itself can live on T, right? That's
Yes.
other thing that you can look at.
Yeah.
Yeah.
The obvious. It would be like replacing ordinals by trees. Or
Yeah,
something
yeah,
like
exactly.
that.
I know one paper where it was looked at, but only for a very restricted class. So yeah, there's not much done there. Hasn't been much done. Yeah.
I mean, you have many ladders to alpha depending on.
Exactly. Yeah. Each node has a
Has a ladder.
yeah. Yeah.
Tree ladders. Okay, thank you, Daniel.